Okay, great. So today we are going to speak about the contraction theorem. This is an interesting theorem that has to do with different things in machine learning. And stop me at any point with questions. For instance, in Markov decision processes, it's used to identify the optimal policy, which is then also used in reinforcement learning for the same objective. And also, it's used also in a declarative manner. So not only to find something in a constructive manner, but to show that something exists. So in game theory, there's a lot of usage of this and other similar mathematical tools to be able to show that an equilibrium, a Nash equilibrium in a game exists and so on. So this is the background to this theorem. Is specifically, it's if you think about the different aspects of the workshop, this is this falls in the optimization and search part. So this is how you actually find, how you do the learning, how you find things when you do the learning. Okay. Okay. So now any questions or comments about the background before I go into the details? Okay. Okay. So and as I go through this, maybe I'll mention a few words about how it connects, but that connects concretely to, say, Markov decision processes and so on, but that's not the objective here today. So the situation that we have is a function, an abstract function from one set to another, but the set has a structure on top of it that represents a distance. Essentially, that means if you look at the axiom here on the right, it would mean that the triangle inequality holds. So essentially, if you think about it, where did I put this here? If this is a triangle, then going directly from one point to another is shorter than going indirectly from one point to another. That's the idea. So that is captured here in this axiom. If you take 2 points, 2 arbitrary points, x and z, the distance between them is less than going through an intermediary point y. So if I go from x to y, and then I go from y to z, that's a longer distance than going from x to z directly. So that's essentially the notion of a distance on a set. Also the other two axioms is that the distance between a set to itself is 0. That is kind of like saying that the objects of the sets are defined. They don't have, there are points, they don't have, they're not part, they are an abstraction. You don't go into them, and they don't have a distance within them and things like that. And also intuitively, if I go from x to y, the shortest path from x to y is equal to the shortest path from y to x. All of these are axioms, so we assume them, and this is called the metric space. So this is a metric space. It's a mathematical abstraction that enables the discussion of the type of functions that we are interested in that will have those equilibrium or fixed points. So essentially, we're looking at functions from x to an x, from a space to itself, that have a metric, have a distance, have a notion of a distance. For instance, in the context of Markov decision process, you have the state, or reinforcement learning, you would have the state of the world, and then you make an action, you get a reward, and you go to another state. So the states of the world are the x in that case. Okay. Any questions up to now?
What is the variable on the page on the left, the 3 lines down? It says 0 is less than something, is less than 1. Is that Q?
Yeah, that's Q.
Okay, thank you.
Essentially, we're getting there, Jim.
Okay.
But essentially, we're talking about contraction. So we're saying that after you apply the function, the distance between any 2 points becomes less. Okay, that's the meaning of contraction.
Okay, thank
you. That Q is like a half, or 1/3. So if you look at the distance between 2 points after you apply the function f of x and f of y, okay, then the distance became smaller relatively to the original distance, you see. So if the distance was 10, now it's 5, if Q is a half. Okay?
Thank you.
Yeah, okay, great. Yeah, so in that situation, when we have a function that contracts the distance, then it needs to be also continuous. I'll explain exactly what we mean by continuous. Then we're going to get a fixed point. What is a fixed point? A fixed point is basically a point where when you apply the function, the point doesn't change. That's a fixed point. Okay, f of x equals x, or f of a equals a. Yeah, the function doesn't change, right? And the idea, think about it as, say we are improving something. Like for instance, in the reinforcement learning, every step tries to improve our estimate to our gain in the future. How much money we're going to gain from this game of making decisions. Okay, so a fixed point would be a point where we make a decision and we don't gain anything more in the future. A reinforcement learning is a situation where I make constant decisions, and mathematically or theoretically, you're making them, basically an infinite number of times. You can think about it that way. So, but we have a discount, so only a finite time is meaningful. That's just a mathematical tool to think about it that way. But anyway, you're making decisions, okay? At some point, you get to a point where whenever you get to a certain situation, you make a certain decision, and that's the best thing you can do, in the sense that you can't improve your estimate of how much you're going to gain in the future. That's a fixed point. Now I'm making decisions, and I know what's the right quote unquote way to make those decisions, and I can't improve them. So you know, the same thing with the game theory situation. I make a decision, and given that everyone else is doing something, I can't improve how much I gain from the game. So that's a Nash equilibrium. Again, it's a fixed point. So fixed points are very much related to obtaining something that we want in a search space. And that's how relevant this mathematical tool is. Now, the other notion we need to understand is continuity. And essentially, continuity, you should think about it as functions that don't have a jump. If you draw them on a piece of paper, if you can do that, they don't have a jump. You don't pick up your hand from the paper, essentially. Now, in this context, we formalize this in the following way. When we have a series that converges to a point x, you see lim xn equals x, then the function f of xn, the function, when I have a series of points, x1, x2, x3, and so on, I can apply the function to each one of them. I get a new series of points, fx1, fx2, fx3, and so on. It converges to f of x. Okay, that's the notion of convergence or continuity. So basically, continuity means that when I get close to a point, the function, I'm applying the function on the series that is getting close to the point, it gets to the same expected point. Maybe a picture here is useful. So if you have this series of points getting closer to some place, okay, and you apply the function, and you get another series of points, okay? You're just applying the function, basically. Then this point here is the point I'm getting close to. I'm going to get close to what you expect, the function of that point. Okay, that's the meaning of continuity. And note that this meaning is, I can define it because I have the notion of a distance, so I can define that in the usual way. I can define anything I want in the usual way because I have a notion of the distance. Okay. Now, there's a distinction, an interesting distinction that we need to understand, and then we get to the point of why this is happening. Why do we get to a fixed point, which is what we want to understand today. So there's a distinction between. Now we just think for a minute about the series. There's a distinction between the series getting close to a point or the element of the series getting close to one another. Okay, so let's think about an example. If you think about a half, 1/3, 1/4, 1/5, where does it get close to? A half, a third, 1/4, 1/5, where does it get close
to? 0.
That's it. It gets close to 0. So we say that the series converges to 0. But now we can say that X, our space, doesn't contain 0, okay? Then if you look at 1 over a half, 1/3, 1/4, they will still get close to each other, but 0 is not going to be, okay? 0 is not going to be there. So it doesn't converge to anything. It just gets close to each other. So we make a formal distinction. We say that a series is a Cauchy series if it just gets close to one another. If it converges, it's like it goes to 0 and 0 is in the space. So we say that a space is complete if every time a series gets close to each other, eventually it converges to some point. So we are not allowing, basically, as part of the conditions here of the theorem, to take 0 out. That's not allowed. Okay, makes sense?
One quick question, Eitan.
Mm-hmm.
So how is the distance coming into picture here in the continuity theorem that you said, and also in this Cauchy?
Yes, so if you look here, to say that to formally say that a series is a Cauchy series, we need the distance here. Let me walk you through this. So it's like we're playing a game, okay, Kritika?
Mm-hmm.
You give me an epsilon. An epsilon could be very small to make it hard for me, okay? So say you say 1 over 60. Now I need to give you a location in the series. So my series is 1 over half, 1 over 3, 1 over 4. I need to go far away, like after 1 over 60, okay?
Mm-hmm.
Far away, I go to 1 over 61, okay? Or maybe more, doesn't matter. I go as far as I need, okay?
Mm-hmm.
So that's the n epsilon. I find a very far away place. Now, whenever you go 1 over n minus 1 over m, where both of them are very far away, if you subtract them and you take the absolute value, which is the distance in this case of the real number, then it will be smaller than 1 over 60, you see. So if you take 1 over 1,000 minus 1 over 1,000 plus 1, absolute value, it will be less than 1 over 60. Okay?
Mm-hmm.
So basically what you're saying is that you are, for any small thing that you're going to give me, for any epsilon, I'm going to find this point in the series where the distances are going to be small enough. From then onwards, at infinity. Make sense?
Okay, got you.
Yeah. And now to the gist of the theorem, okay? So basically what we say is, okay, give me any point in the space and assume that when the series gets close to each other, then it goes to some point. That point, we'll use that. That's the completeness. So take any point in the space, and now start applying the function. Apply it to the point, and then apply the function to what you got, and so on and so forth. So you're just taking any point and then applying the function, and then applying the function again, and then applying the function again, and so on and so forth. Okay? Then that series will converge to a point that is really interesting, because if you apply the function again on that point, you'll get to the same point, fixed point. Okay? So that's the theorem. Now let's see how we prove it. It's very easy. So what we do, the basic thing to understand is this line. The rest is simple and easy. So what is this line? So an plus 1 and an is just applying the function n plus 1 times to the first point, and an is applying the function n times. Now, because of this rule, we get that it's less than q times an, which is applying the function one time less, the distance between that, and an minus 1, applying the function n minus time. Okay, because of this rule. You just substitute here to get an plus 1, you substitute x with f, with applying f on x0 n times. And that's how you get an plus 1. To get an, you substitute y here with applying f on the first point n minus 1 times, and so on and so forth, every place here. So you just, by applying this, you get that the distance between two consecutive points is less than q times the distance between two consecutive points that happened previously. And you just keep on applying it recursively. And then you get that this is something very small, because q is like half. So it's half to the, power, any number here. So it's going to 0. So basically, you see that it's like a Cauchy series, because two consecutive points in the series are getting closer and closer. But actually, you want them to be from a certain point, any two points. Okay. So for that, you need to use the triangle inequality that I told you about. So you say a7 minus a4 is less than a7, the distance less than a7 minus, the distance between a7 and a4 is less than the distance between a7 and a6, plus the distance between a6 and a5, plus the distance between a5 and a4, and then you apply the recursive step that we did before. So basically, here you're using the triangle inequality, and here you get something that is actually going to 0, basically. You just need to remember this sum, 1 plus q to the square and so on, that you've probably seen before. If you don't, just search it up. But it basically, you can see now easily that it goes to 0. So essentially, what happens here is that the series is a Cauchy series. Therefore, it's converging because we assume it converges. And the last step is to use the fact that the function is continuous. So now we have that the series that we're talking about goes to A. Then if we apply f to the series, it just changes the first element. So the series still converges to the same thing. But because it's continuous, it converges to f of A. So f of A is equal A. Again, the series converges to A. That's what we just showed. So if you apply f to the series elements, you get the same series, but the first element. Because if you remember, the series looks like x, f of x, f of x. But if I apply f here, it's this element, it's f of x. If I apply f here, it's this element. So this one remains the same series, but the first element. Now I know that this one converges to f of A. Okay. but it's the same series, but one element. So f of a equals a. Because if you have a converging series that you change a finite number of elements, it converges to the same place. It doesn't matter. Anything that happens in the beginning of the series for a finite number of times doesn't matter when you consider convergence. So that's essentially the contraction theorem. Very, very important and interesting tool, which has a lot of generalization. But that's the basic idea. Any additional questions or comments? Okay. So as I said, we are reigniting the workshop, so expect more content and ask more questions. And we'll continue next time. Thank you.
Thank you, Eitan.
Yeah, thanks, Eitan.
Thanks.
Thanks, Eitan. You'll make the recording available.
Yes, of course.
Thank you.
Thank you. Bye-bye.
Bye.